The next network problem in this chapter is called minimal spanning tree or minimum spanning tree. And the objective in this problem is, again, like previously, you have nodes and the nodes are connected by edges or arcs. Now the objective here is to connect the nodes, okay, with the minimum number of edges, or if the edges have weights, then with the edges such that the weights of the edges used to connect all the nodes is minimum. So this is called minimum spanning tree, a set of edges that spans the entire tree such that all the nodes are connected. And the reason why it's called a tree is because at the end, when you finish solving the problem, you have something like a tree where there are no cycles. As you will see, I will show you in just as when we finish solving the problem. So um, the let's look at a brief example, and then we'll come back and then look at the steps. Okay, so here in this example, so we have a construction company that has built a neighborhood of homes. Now we want to connect these homes in such a way that the cost of connection, and we want to connect for sewage and water and electricity and so on, utilities. So we want to be able to go from one node to another. All the nodes need to be connected to the system, and each node has several, neighboring nodes that you have distances for those between those nodes. Okay, so we want to be able to reach all the nodes in the system, but we want to use edges such that, so since the edges have weights in this case, you want to add up all the weights of the edges, and that sum of the weight of edges used to connect the nodes is minimum. Okay, so the practical application for such a problem is as this example suggests, homes to be connected with utility lines, or you have to dig ditches and lay the lines, the water line and electricity, and so you want these distances to be as small as possible, and yet connect all the homes. And it could be cities there. You want to be able to reach the cities with say fiber optic cables, and you want these cities to be connected with minimum distances of fiber optic cables and still connect all the you're not really interested, you don't care how fast you go to a particular node. The thing you're interested in is that all the nodes get connected with the minimum cost. So that's the application here. So this could be neighborhoods in a city where you want to connect with fiber optics, or whatever that may be you're interested in. And this problem can be modeled as a linear programming model and solved as a linear programming problem. But there is an easier approach, and the linear programming model can be really complex. So it's not really beneficial for us to set this up as a linear programming problem, but look at it as a graph problem. And there is a very elegant, very simple, and fast algorithm available for us to find the solution. And it goes like this. That is, you select any node in the network. It doesn't matter, arbitrarily select a node, and then look at the edges for around that node. Okay, say for example, here is node 1, and there are 3 edges, right? And the algorithm says that select the one that has the smallest weight. Okay, connect this node to the nearest node that minimizes the total distance. Okay, so now you have 2 nodes that are connected and the rest of them are unconnected. So now you look at all the edges from the connected nodes to non-connected nodes and select the one that has the least weight. And you keep proceeding in this fashion And if there are any ties, you can break the ties arbitrarily, okay, and proceed until all the nodes get connected, and you're guaranteed the least weight or least distance edges selected that connects all the nodes. Okay, let me illustrate the algorithm with this example. So we start with a none of the edges are connected, and we have the distances. Okay. Now you can arbitrarily select any node here that you like. It doesn't matter where you start. So let's say that we start with node 1. Okay, so node 1 has been selected. Okay, so now you look at the edges emanating from node 1 and select the one that is smallest weight. So which is that edge. So you select that edge. So once you select that edge, now 1 and 3 are now connected. So 3 gets connected. Now you look at all the edges going out of these connected nodes. So if you look at a cut like that, okay, so you see the edges going out of the connected nodes are that, 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 and that, and this is the smallest weight edge. So you select that edge next. Okay, so now node 4 gets connected to these two nodes. So now you have these three are the connected nodes, and all the rest are non-connected. So now again look for a cut. Okay, so that's a cut separating the connected nodes and the non-connected nodes. And in the cut, look for the smallest weight edge. And here we have 3 of them that has the smallest value 3, and it doesn't really matter which one you select. You can arbitrarily select any one of them. It doesn't matter. So let's say we select that one. Okay, so now 2 gets connected to the connected nodes. So these are the connected nodes and these are the not connected nodes. Now the cut is going like that. So this is the cut that separates connected and the non-connected nodes. Again, look for the weights 3, 5, 7, 3, and 6. And again, so there are 2 of them with the smallest weight. Select any one of them arbitrarily. So we say we select 2 to 5. So now 5 gets connected, okay, to the already connected nodes. Okay, so that gets connected. So now the cut is going like that. So this is the cut that separates connected nodes and non-connected nodes. So 4, 7, 3, and 6. So select 3. Okay, so the edge with weight of 3. So now 6 gets connected. Now at this point, the cut that separates the connected nodes and the non-connected nodes is this. So we have these 3 nodes, of which this is the least weight, smallest weight edge. So we select this edge. So now 8 gets connected. Now the cut is this, and these are the 3 edges separating the connected and the non-connected nodes, and that is the smallest weight edge. So that connects with 7. Now all the nodes are connected. Now this is called the minimal spanning tree. So here there are no cycles. You see, there is you will never see a cycle with any set of nodes. It'll all be just what one would call as a tree branch going, and it'll never come back and connect to the tree again. So the edges selected. So edges 1 to 3, distance of 2, 3 to 2, okay, 3 to 4, 2 to 5, 3 to 6, 6 to 8, and 8 to 7, giving you a total distance of 16, and you're guaranteed that that 16 would be the minimum possible distance.